So all the formulas are usually some process that has been generalized for you. So let's say that this was my equation and I was solving by completing the square. So a little review about completing the square. And there's no numbers up here, so it's going to look a little different. So first of all, to complete the square, we need to make sure the constant is a perfect square that we want in our polynomial. I have no idea what c is, so I'm just going to assume that it's not the number that I want, and I'm going to make sure I put something there that is what I want. So first thing I would do, let's run into the trash can, is move the c to the other side. So I would subtract c from both sides. Okay, so I have minus c on the other side. Okay, the next thing I would do is that I can't complete the square when there's a coefficient here. Okay, so I'm going to go ahead and divide both sides by a so that this coefficient is no longer here. So I would have x squared plus b over ax equals negative c over a. Now remember, my goal is to complete the square and solve it that way, so I want to make the left side of the equation a perfect square. Now I know that might be a little confusing because there's no number here, but what's the process we used to pick the constant at the end? Elijah? Good. So divide this middle term by 2, and dividing by 2 is the same thing as doing what? Multiplying by a half, so we're going to do this. And then we have to square it, right? So we're going to get b over 2a, and we're going to want to square that, which is going to give us b squared over 4a. Is that okay with everybody? So it's not numbers, but same idea. I took this, divided it by 2, and squared it to decide what I want to add right here to complete the square. Oh, yeah, a squared. Thank you. So I'm going to add my b squared over 4a squared. And I'm going to add it to the other side, too. It wasn't being multiplied by anything, so it was that same exact amount on both sides. Now, remember our purpose in completing the square. This should now factor as a perfect square. Okay, so it should factor as something squared. X would be the first term of the binomial. And then over here, it would have to be b over 2a, because if you square that, you would get b squared over 4a squared. So that's that side being factored. On the other side, I would like to combine the fractions together, but to do that, they need a common denominator, which means for this denominator to become 4a squared, it has to be multiplied by 4a. So I'm also going to multiply the c by 4a. So that's going to become minus 4ac. Okay. So on this side, I have a denominator of 4a squared. And I'm just going to put the positive term before the negative term. So instead of writing negative 4ac plus b squared, I'm going to write b squared minus 4ac. Okay? Hopefully things are starting to look a little familiar. Okay? Once we create the perfect square, how do we solve the equation? How do we get x alone? Jarrett? So we're going to take the square root of both sides. Okay? So on the left side, we're just going to get x plus b over 2a. On the right side, we're going to get plus or minus because we took the square root of both sides. In the denominator, the square root of 4a squared will be 2a. And I don't know the square root of b squared minus 4ac. And no, you can't say, well, the square root of b squared is b. I know that part. These things are being subtracted. So if they were being multiplied, you could separate them factor by factor, but not with subtraction. So this is going to have to stay all underneath the radical. All right, so what's the last thing I have to do to get x alone? Correct? Good. Subtract b over 2a on both sides. So then I'm going to get x equals negative b over 2a plus or minus the square root of b squared minus 4ac all over 2a. Notice those fractions have common denominators. So another way to write this would be negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay. What is this? The quadratic formula. So they didn't make up the formula. What they said was completing the square gets old, right? So imagine if nobody came up with this formula yet, and every time you wanted to solve a quadratic that wasn't factorable, you had to go through the process of completing the square. That would get old pretty fast, right? So basically, they're giving you a formula that says, hey, since you can do completing the square every time, you can just do this every time. Okay? Because this is all the steps of completing the square, but just written in one big thing for you. So the reason why we were looking at all those problems and we might have felt like, dude, I would never solve using completing the square. I would just factor or use the quadratic formula, is because the quadratic formula literally is completing the square, but all packaged in one formula instead of step by step. Okay? So just kind of like showing you guys the connections that people don't just make up the formulas. They actually come from a very solid mathematical background. Okay? All right, the next thing we're going to talk about is the discriminant. So I'm supposing that you guys can use the quadratic formula. So we're going to talk about the discriminant. So first thing I want you guys to do is grab a calculator for these 4 equations. Before you guys get up and go to the back, let me just finish. For these 4 equations, you don't have to answer what the discriminant is yet. But I want to see a sketch of the graph. And it says highlight the x-intercept. So just make really bold on your paper where the x-intercepts are. So 4 graphs are what you're going to get off the calculator. And I just really want you to fill in where those x-intercepts are. Tell me the number of solutions that you have. And by type of solution, I mean, are they real, rational, and you might not know yet, so you can leave this column blank too. But you should definitely be able to fill in this column and this column just by sketching the graph from the calculator and counting how many x-intercepts the graph has. Does that make sense to everybody? So real quick, like 5 minutes, just get a graph, sketch it, here's the intercepts, go. Okay? Make sure if you're borrowing a calculator that you... Here's what our graphs generally look like. So concave down parabola, how many times does it cross the x-axis? 2. So the number of solutions it has are 2. And these are 2 real solutions. Our real numbers are on our graph axes. Here's a parabola, concave up. How many times does it cross the x-axis? So again, this also has 2 real solutions. This parabola, okay, concave up, but how many times does it cross the axis? Once. So it has 1 real solution. And this parabola, concave up, how many times does it cross the axis? 0. So it has no real solutions. Okay? Now, the discriminant is the part of the quadratic formula that would determine how many solutions you have. So you guys don't have to write this down, but a little piece of information. The quadratic formula looks like this. I'll go back to that page, so don't freak out. Okay, so the quadratic formula looks like this. So if I'm plugging stuff in, okay, how would it turn out that I only have 1 solution instead of 2? So you plug numbers in. What's going to have to happen here to only have 1 solution instead of 2? So you're going to have like a number here, plus or minus whatever's underneath the radical here, then like a number down here. Okay? Yes? Okay, it would be a perfect square trinomial. That's true. So it would factor and only 1 factor would cross the axis. What would happen in this formula, though? So if you put a number here and you add and subtract something from that number, you're always going to get 2 things, right? Except for when. What can happen here that you're not going to, when you add and subtract, you're still only going to end up with 1 solution instead of 2? Yeah? So if it's 0 in here, right? That's how we'll just get 1 solution. Okay. And so when we look back at what we were looking at before, in order for there to have only been 1 solution, then the discriminant had to be equal to 0. So the discriminant is what's underneath the radical in the quadratic formula, not including the radical, just a number. So the discriminant is just a number. It's the number you get by doing the b squared minus 4ac part. So when that part equals 0, you would expect your parabola to hit the x-axis 1 time, meaning it would have 1 real solution. Okay? that solution would not only be real, it would also be rational. The reason that it would for sure be rational is because rational numbers can be written as a fraction, and if the stuff in the square root is equal to 0, you don't have a square root, so you're just going to have a number over another number. That's a fraction, so it can definitely be written as a fraction, which makes it rational. Okay. All right, what has to happen in this for there to be no real solutions? What has to happen during your calculation for you to say no real solutions? Jarrett? The bottom could be negative and there could still be solutions. CJ? The number underneath the radical is a negative number. So if the number underneath the radical is a negative number, that's when we stopped calculating in Algebra 1 and we said no real solutions. Okay? So going back here, when this had no real solutions, that meant our discriminant equaled some negative number. Okay? If we have no real solutions, so the types of solutions, there are no real ones, but it turns out that means that there are still two solutions, but they're called complex, and we'll talk about in a minute what that is. Okay? So two complex solutions. All right, so why do we have two of these? Well, in both of these cases, there are two solutions, which means, keep doing that, the number underneath the radical exists. And so what's happening is you're taking a number, you're adding that, getting one thing. You're taking a number, subtracting it, and you're getting something else. Okay? The reason it's divided into two situations is the kind of number that you get. So looking back here, if I calculate the discriminant for this real quick, 7 squared minus 4 times negative 2 times 10. Okay? So that's 49 plus 80. So it's 129. So this is positive, but that number's not very special. Okay? However, if I calculate the discriminant here, it's 7 squared minus 4 times 1 times 6. Okay. So that's 49 minus 24, which is 25. Still positive, but what do you notice about this number? It's a perfect square. So what does that mean for us in the quadratic formula? Yeah, do we need are we going to be able to simplify the radical part if it's a perfect square? Absolutely. If it's not a perfect square, there's always going to be that radical part that exists in your answer. Right? So the reason that's important to us is even though these both end up with two real solutions, if the number's a perfect square and you can simplify the radical, those are two real rational solutions. Meaning they're going to be those nice numbers that can be written as a fraction. Okay? When you have a number underneath the radical that's not a perfect square, even if you can simplify it some, you're still going to have something left under the radical because it's not a perfect square, which is going to make that kind of solution irrational. So the difference here is even though you see it crossed twice, these ones are going to plot at numbers that you could probably plot nicely on the graph when they're rational, and these ones are going to be the ones that would be harder for us to interpret or figure out where they were. We could estimate where they were, but okay. So your discriminant doesn't solve the problem for you. It is this calculation, and it just tells you about the roots of the solution. But look at the connections that tells you. If you know the lead coefficient and you know how many solutions you have, you should be able to make a little sketch of the graph. You wouldn't know exactly where it crosses, but you could draw it concave up or concave down and crossing the axis the correct amount of times based on that information. Okay, so the discriminant can do that for you. All right? Any questions about what the discriminant is or what it tells you? No? Okay. So it doesn't tell you the solutions. It tells you the kind of solutions that you have. Okay? All right, so now let's talk about when we're in this area of complex solutions. All right. So what is this whole complex number idea? So you guys are used to this world of numbers that looks like this. Maybe you don't like it in this format, but you see the world as, let me not write it there. There are real numbers, and every number you know, unless you already know about the complex number system, is a real number. And then within those real numbers, there are two categories. So it's basically split down the middle into either rational or irrational numbers. And then we have lots of subsets that we like to label within the rational numbers. So if you're rational, you could also have a subset within there that's the integers. And then within the integers, there's a subset of numbers called whole numbers. And within the whole numbers, there's a subset of numbers called natural numbers. Sorry, can't fit the word. Okay, so this is how we see the number system. However, real numbers are just part of a bigger system called complex numbers. So a real number still exists within that system, but then it has this clear separation that besides the real numbers, there's this category that could also be included called imaginary numbers. Okay? They're not made up, okay? But they have a funny name. All right? I guess if in today's day and age, if I had to label them, I probably wouldn't call them imaginary just because of the lashback of the teenage population when you call them imaginary numbers. All right? So basically, we're tacking on another set of numbers right here, and you can use these two numbers together in what we call the complex number system. Okay? So for example, imaginary numbers are going to have this little I attached to them for the symbol. Okay? So something like 4i is not 4. It's an imaginary number, and it's 4i. Something like 5 plus 4i is a complex number, and the complex number has a real part to it, but it also has an imaginary part to it. Okay? So that's why you'll sometimes hear people say imaginary and sometimes say complex. Imaginary usually refers to specifically using the I with the portion, and complex means, yeah, it can have that, but it could also have this real part with it also. That's a question? Or just stretching? Stretching, guessing? Okay. All right. So here's how it works, and here's how it was defined. So there are places in math where you come across this square root of a negative. In some places, you can just dismiss it and move on with life, like you always have done in Algebra 1. But in other places, okay, there is a need to get to the end of the problem. There is a need to be able to use that because in the end you know that it's supposed to turn out to be real, but you got to this part where it doesn't fit the real numbers anymore. So they had a need to create a bridge in between. How do I finish a calculation with this? So basically, we used to stop when there was a negative underneath the radical, and now a negative underneath the radical says I. So like if I see a square root of negative 4, okay, I know, I'm going to split this up into two things. Oh, that's not really going to work. Okay. It just changed it. All right. All right, we're going to think of it as, sorry you guys, I just changed the battery, I promise. Okay. The square root of negative 1 times the square root of 4. You know the square root of 4 part. What's the square root of 4? 2. It's the fact that it's being multiplied by a negative under the radical that's a problem, and we would normally dismiss it. But now we're not going to dismiss it. We're going to call this square root of negative 1 I. We know the number part of that, and this would be called 2i. So you simplify the radical like you would normally simplify the radical. That does not change. The difference is you can now simplify a radical that's negative by not writing the negative in the radical and instead writing the letter I. And then everybody knows you're talking about having a negative underneath the radical. Okay? So the way that they came about this is they didn't really originally define this. They more kind of originally defined I squared. They basically wanted a number that when you square it, it makes a negative. Okay? But if I walked in here and said, I'm thinking of a number, when you square it, you get a negative, you guys would all tell me that doesn't work, right? They needed that to work. So they said, I'm going to make up a number called the imaginary number, okay, I. And when you square it, you're going to get a negative, okay? So they made up this part right here. When I take I and square it, I get negative 1. Okay? So notation-wise, what do you write and what don't you write? You still don't leave negatives underneath radicals. If you see the negative under the radical, you write it as I, okay? But when you see I squared, you don't leave it as I squared because it's really equal to -1. And so this is why this number system, like we could all go make our own number system. Okay, we can make up some name like imaginary, give it a letter. We can make up our number system. Most likely no one would use our number system, okay, unless you had a really cool group of friends that really wanted to buy into your number system, okay? People continue to use this number system because it's actually useful in specific areas of mathematics because there's a need for this connection for something squared to equal a negative. Because that need exists, this number system still exists. Okay, someone didn't just make it up to play around. They made it up because there's a mathematical need for it. Okay? So then the cool thing is the imaginary numbers are not disconnected from the real numbers. This is their connection. If you square an imaginary number, you get back a real number. So like I have a shirt. My sister gets embarrassed when I wear it in public places. But my shirt says this. Okay? My shirt's funny. I have worn it before. Okay. So my shirt is funny. That's a joke. But she doesn't like when I wear it in public because she thinks most people don't get the joke and they just think I'm very strange. But that's okay. So it's a joke, and we'll talk more about why it's a joke right there. But it's because these are complex or imaginary number parts, right? But when you multiply them out, guess what you get? A real number. So that's the cool part about complex or imaginary numbers. They don't stand isolated and alone. They actually connect back to the real number system. So here's how it works. Now if I see I to the third, okay? Think about I to the third. It's like having an I squared and then multiplying it by another I. But what did we say I squared was equal to? -1. So -1 times I would be negative I. Now we do write single i's because we don't revert back to writing negative numbers under the radical. Okay? But we don't write any higher powers of I with I because they turn into real numbers. So like I to the fourth is really like having an I squared times another I squared. And what is each I squared worth? -1. What is -1 times -1? Okay. All right, so I want you guys to see real quick if you guys can simplify these things. If you know it, let your group try to figure it out first. So, I to the 5th, I to the 6th, I to the 7th, I to the 8th. Take a couple minutes and see. I don't know any math jokes. All right. I to the 5th. Somebody raise your hand. Tell me what you got. Dylan. I to the 6th. Quentin. I to the 7th. Maya. I to the 8th. Jarrett. Okay. So you already told us all. I figured you could tell us again. Okay. So if you aren't sure how we figured this out, basically my idea is once I squared equals -1 is cool, and I really have to know that. But in this certain circumstance, once I knew that I to the 4th was 1, I would basically try to write all of these with as many of those as possible and then just look at the leftovers. So like I would think of I to the 5th as being I to the 4th times I. And so like this part would turn into 1, and then I would just have left I. Like for I to the 6th, I would think of it as I to the 4th times I squared. This part turns into 1. And 1 is a beautiful number to use in multiplication because it basically becomes kind of unimportant, right, compared to the other factors. And I squared is -1. So that's what I'm left with. So applying that strategy here, I to the power of 231, okay, how many I to the 4ths could I list there? How would I figure that out? What arithmetic am I going to do to figure out how many times I to the 4th would be used in I to the 231st power? Dylan? I divide. Okay, so I'm going to take 231 and divide it by 4. Okay, so 4 goes into 231 57 times, with 3 left over. That means I can use I to the 4th 57 times. But that doesn't completely give me 231, right? Because I still have 3 left over, so I need 3 more powers of I. What does this part simplify to become? What's I to the 4th? So those of you that are struggling, look back. I to the 4th is 1. 1 to any power is still going to be 1. So all of these I to the 4ths just turn into 1. And basically what's left right here tells me my answer. I to the 3rd power, which is the same thing as negative I. So what are you going to want to have trapped away in your head, in your memory about imaginary numbers? Those first 4 powers at least, right? Okay, so this becomes negative I. All right, so I to the 120th power. Okay, how many I to the 4ths could I use to create a power of I to the 120th? 30. Is there anything left over that I need to include? No, that makes all 120 powers of I. So, nothing extra over here, which means I to the 120th power is really equal to 1, because it's the same as I to the 4th being used over and over and over again with nothing else, so just 1 times 1 times 1 times 1 times 1. Okay? So, idea that I want to lay today. Do you know now what an imaginary number is? Okay. So it shows up when we have negatives underneath the radical. We're going to simplify our radicals as normal, but with a negative underneath. And they have this pattern that exists among them that connects them back and forth between the real numbers. Okay. So real quick in your groups, rewrite the number square root of negative 24 using I for 2I. Rad 6. And you guys even put the I in rad what? 6? Good. You guys even put the I in the right place. Now, if you put the I at the end of the 2 rad 6, it's not really a big deal. You're right. The problem is I is such a skinny number that when you write it at the end of the radical, sometimes it's really hard to tell if you're saying the I is in your radical or not. So though we tend to use it like we use X, you would do the same thing with X. If you want to write 4X, you just write 4, and then usually we write the X after the 4. If you wanted to write 4 rad 3 times X, we normally don't write it necessarily like this, because again, it's like, where is the X? Is it part of the radical or not? A lot of times you would see that written this way too. So it's just kind of like etiquette. You'll probably see it written this way most of the time. If you put 2 rad 6 and then you wrote I, and I could clearly tell your I was not inside your radical, your answer is just as correct as this, okay? So you simplified the rad 24 as normal. The I is there because the negative was in the radical. Okay? Yes? 6I times 2. So the 6 can't come out of the radical because when you break down 24, you only get a perfect factor of 4. So that's why 2 is outside the radical, but the rest of the factors are still inside the radical. Okay? Other questions? Yes? You can't do 24I. Basically, what's happening is when you see the square root of negative 24, it's like the square root of negative 1 times the square root of 24. So this part is producing the fact that there will be an I outside the radical, but this part needs to be simplified how you would normally simplify a radical. Okay? Other questions about that? Let's see what else we have here. All right, so I solved a bunch of these last time, right? So this is what I'm talking about. Once you learn what the imaginary number is, it's just like all these little checkpoints, like, oh, can you use it now? So like, do you know that square root of negative 24 has an I in it? Good job. Like, what if you go to solve an equation like this? So if you go to solve this equation here, 3x squared plus 12 equals 0, we would move the 12 to the other side. We would get then that x squared equals negative 4. So normally at this point, you would kind of stop because you would have a negative underneath the radical. But instead of stopping at this point now, we would look at this, and it would kind of depend on the directions. It just says solve each equation. So I would finish solving. Sometimes it'll say find all the real solutions. If you're only looking for real solutions, do you need to keep going at this point? No. But if it just says solve or it says find all the solutions and they're not real specific, I would just be thorough and find everything, including complex solutions, okay? So in this case, I would use everything I knew from before. And then my final answer, I would incorporate the imaginary part. So square root of 4 is 2. And then I, because of the negative in there, so this is 2 complex solutions, positive 2i and negative 2i. Okay. Is that all right with everybody? Yes, no, yes. Okay, so tonight's homework number 9.